Well, hi, folks. Mr. Bleeker here. In our third and final installment, final lesson on the excretory system, what I want to focus on is the kidney as a blood pressure maintainer. Now, if we think about homeostasis, that's maintaining a constant internal environment, your kidneys are not just a filtration organ. In fact, they have a very important role in maintaining your blood pressure. So I need to paint a scenario for you. Imagine that someone's in a car crash and they're hemorrhaging, they're losing a lot of blood. As you lose blood and your blood pressure dips, you can be rendered unconscious by a lack of blood flow to the brain. Now, that's definitely not in the survival interest of anyone. If you're hemorrhaging or bleeding, you need to stay conscious as long as possible to stem the bleeding so that ultimately you don't pass away. Now, we'll focus in and examine how the kidneys will fight alongside you to help keep you conscious, how they'll fight alongside you to keep your blood pressure elevated. But first, we need to figure out, how do they know what your blood pressure is? So this is where airplay comes in. And I'll go to our notes and I'll go to, there we go. I should be seeing it now. Make sure I'm just not mirroring. There we go. This is what I wanted. This slide, which denotes kidneys as blood pressure devices. So the first thing we'll look at, zoom in here, is this part, this part of the glomerulus. Now, at that intersection, let's move this over. There we go. That intersection is very important. Now, you'll recognize this because this is where the afferent arteriole comes in and the efferent arteriole leaves after the ultrafiltration. Let's just draw. I don't like that color. Let's go with nice green there. Let's take this new app out for a spin. Good. Let's look at this region right here. It's very pressure sensitive. And these cells are feeling the pressure of the blood pushing against the wall there from the afferent arteriole, and they'll also feel the pressure of the blood as it leaves, and they'll feel pressure from pushing from the efferent arteriole. Okay, so they're pressure sensitive and they know that there should be quite a bit of pressure because this is ultrafiltration and that's a lot of blood flowing in. Remember, this is coming from the renal artery, which is hooked right up to the descending aorta. That's a lot of pressure. Let's erase. You might wonder what this is here. And this is the distal convoluted tubule. Now, if it's not obvious, here's the proximal tubule. And as we come around, we get to the distal tubule. And you notice that the distal tubule right here is very, very close to the afferent and efferent intersection. And this region of cells, actually, let's switch that color. Let's go with that. That'll work. There's a region of cells right here in the distal tubule, and they're very pressure sensitive, and they should feel a lot of filtrate. So as you filtrate, and you'll probably be thinking of your urine is forming, it should be pushing, of course, against the walls of the distal convoluted tubule. Now, if you hemorrhage and you're losing blood, there's not going to be a lot of filtrate produced, so there'll be less pressure in the distal tubule. And what I'm telling you is the distal tubule will notice. So I'm going to just zoom out here. And what we have to look at is how these pressure sensitive cells respond. They send both of these cells in this area And let's clear this. These cells in this region, I want a different color. Light blue is better. Cells in this region are known as the juxtaglomerular apparatus. Now, that's an interesting term. What it means is juxtaposition means to sort of be beside somebody or to be adjacent. These cells are near all the action, where all the pressure is happening. And they'll know what's going on. And they'll respond by sending out an SOS call. Now, their SOS call is kind of, this will go in a few stages. So I'm going to come back to airplay when we're done, and I'll fill in all these notes. But I want to show you an animation which I think really describes this a lot better. I'm just more of a fan of animations these days. Okay, so iPad, you can go to sleep for a little bit. And here's what we're looking at. Now, the glomerular filtration rate, typical glomerulus is about 120 milliliters per minute. And sort of under natural, normal sort of arterial pressures. So if we look at the afferent arteriole here, the blood will flow into the glomerular knot. We should be getting about 120 milliliters from a typical glomerulus. Now, when the blood flows out of the knot and out the efferent arteriole, this is the region right here I'm tracing with my cursor, known as the juxtaglomerular apparatus. And as I say, it should be under pressure. But it doesn't always stay that way. So first part of the animation here, this is what we would normally expect. Normal pressure here out the distal tubule. So these cells would be sensing normal pressure. But what if a person's hemorrhaging and there's a blood flow decrease? Now you can see the glomerulus is going to be experiencing a lot less pressure, so you'll get less filtrate. And your filtrate level dives. Now if you look over here at the filtrate, it won't be pushing against the walls of the distal tubule, and the distal tubule is going to notice. It kind of becomes an issue. Now, these cells and these cells here will secrete an enzyme, and it's a very smart. Just going to make sure I'm still recording here. Yeah, it's still going. It's actually quite smart. Let's see here. There we go. It sends out an SOS call. Now, in order to get the hormone that'll make this, will basically solve this problem. Let's see there. Just give it a second. We should get the secretion of an enzyme known as renin. Now, what renin does is renin will be secreted into the blood. Let's see if I can get this. Sorry, folks, the animation is just pausing, so just waiting for it to show. There we go. And the person's hemorrhaging, we get a decrease. Okay, so I think I have to go to, there we go. I'll have to go to this portion of it. Just a second here. No. Sorry, I was in the wrong part of the animation. Okay, so this is the part I wanted to show you. An enzyme will be secreted here. So there's a hum of activity. There we go. And the juxtaglomerular cells will secrete an enzyme known as renin. Now, what will represent renin by is these little protein scissors, right? Enzymes can facilitate chemical reactions. And what will happen in this case is the secretion of this enzyme goes out into the blood. And of course, this is going to flow out the efferent arteriole, and that gets out into the bloodstream proper. Once you get out into the bloodstream, there's a dormant enzyme known as angiotensinogen. And if you ever see the ogen part, that indicates that an enzyme is inactive. Renin cuts it. So let's just watch that again. Basically, renin chops off a portion of the molecule that's causing it to be dormant, and now we have angiotensin in its first form. Okay, so what happens? Well, you've got angiotensin 1 floating around in your system, and floating around in your system, well, blood gets to the lungs, and that's where the magic happens in the next stage. When you get to the lungs have a hormone which will act on angiotensin 1. This hormone, or this enzyme known as ACE, or ACE for short, will activate angiotensin to its second form, known as angiotensin 2. Again, this happens in the capillaries of the lungs. It's thin enough tissue for the enzyme, obviously, to make it through to angiotensin 1. Point is, angiotensin 1 is now angiotensin 2. Now, in a trip back from the lungs, believe it or not, we get back to this little flap of tissue. Now, this flap of tissue is your adrenal gland. Everybody looks at the adrenal gland and says, "Woo, that's for secreting adrenaline, epinephrine, right? That super strength hormone." Well, that would be true. That's for that brown region. Okay, known as the medulla of your adrenal gland will secrete adrenaline. But that's not what we're focusing on here. Watch this again. When angiotensin 2, which has been activated by the lungs, gets here, ooh, look at all the aldosterone. Now, aldosterone is a hormone that is secreted by the adrenal cortex. Now, notice I said cortex. So that's the outer portion of the adrenal gland. You see, the kidney can't produce aldosterone. That's not the kidney's, the kidney doesn't have the ability to do that. It's only the adrenals that are on top of the kidney. You would think that the kidneys could just sort of knock on the adrenals door and say, "Hey, could you secrete aldosterone?" But it doesn't work that way. This basically has to involve the bloodstream. So it's been sort of a convoluted path of activating a series of enzymes until we get to this point. Once aldosterone is produced, what you need to know, aldosterone itself will cause the blood to absorb more water. How so? Aldosterone increases the saltiness of the adrenal medulla even more. And when the adrenal medulla becomes, or not the adrenal medulla, my apologies, increases the saltiness of the medulla of the kidney tissue. So as the kidney tissue becomes more salty, it will water chases salt, and more water will end up in the blood. That's really the whole game. There's also another additional effect. Aldosterone, well, really, when you think about this whole enzymatic pathway, what happens, you get water reabsorption. Okay, that's smart, and that happens at the collecting ducts and at the loop of Henle. Okay, that's where water absorption is sort of amplified. So raising the amount of water that's being reabsorbed will help elevate your blood pressure. But an additional side effect of this whole sort of enzymatic pathway is there's vasoconstriction. So think of it as tightening the pressure on the arteries and the arterioles. And if you squeeze on the arteries and arterioles, that helps to raise the pressure even more. Think of it as like squeezing a pipe, and it raises your blood pressure, and that helps to keep you conscious, keeps the blood flowing to the brain, because remember that you're hemorrhaging. So the overall effect, really, we start here, and you see the alcohol. I'll give it a second. There we go. The juxtaglomerular cells, you can refer to them as a group. That's just fine. Send out renin. Renin makes its way out into the bloodstream. Angiotensinogen is activated, becomes its first form, angiotensin 1. Angiotensin 1 makes its way to the lungs, is converted into angiotensin 2. And that is what gets a whole ball rolling with aldosterone. And it's this hormone that raises your blood pressure by increasing the amount of water you reabsorb. Of course, while all this happens, you also get vasoconstriction, which raises your blood pressure even more. So there you go. What you're looking at is an enzymatic pathway that turns on a hormone. So that's it, ladies and gentlemen. That's really how this enzymatic pathway works to turn on, essentially to turn on hormone that will raise your blood pressure. So I think there's just one more aspect of this. I just have to finish filling in the notes. So one moment. Go back to our notes. Make sure you have those in place. Without making a mess. There we go. And mirroring is on. Okay. Make sure my new stylus is activated. Good. So the animation covered steps 1 through 4 with the sensing of the change in the blood pressure. So we'll highlight that. And the juxtaglomerular apparatus, make a note of renin, that's phase 1. Renin produces this, or basically gets this enzyme going, and it's at your lungs right here where the second form is instantiated, and it's angiotensin 2, believe it or not, is sort of the last domino to fall, that gets aldosterone to be secreted, which is essentially what raises your blood pressure. Simple, isn't it? That's a beautiful thing about anatomy. The human body is wondrously complex, but it's doing something very simple here. It's a homeostatic response to raise your blood pressure. And ladies and gentlemen, that's it. I am all out of slides. Okay, so thanks for listening. That is the last part of the excretory system. And have a good one. Thanks, folks. Ciao.